Okay, let's get started. Question 3. I'm really tired, I've been recording for 2.5 hours at this point. Yeah. Anyways. Okay, we have an AC source, some impedances. For each impedance, determine whether they are resistive, capacitive, or inductive. Okay. So let's look at Z1. Notice that Z1 is a real and positive number. Okay, let's look at the general cases. So let's look at the formulas for resistor, impedance for resistors. It's just resistance, right? And what is the impedance of capacitors? It's 1 over j omega c. And then what is the impedance of inductors? J omega L. Now, take a look at Z of R. Z of R is given by the resistance. And we know that resistance is always a positive and real number. Okay, it's not a complex number. It's not an imaginary number. It's a real number. Okay, so look at Z1. Is it positive and a real number? Yes, it's just 10. 10, there's no imaginary, there's no j's, there's no i's. It's just a positive and real number. So this is resistive. Then same with Z2. Both Z1 and Z2 are resistive. Now, the trick comes with Z3. Let us take a look at Z of L. You notice that, okay, fine, there's an imaginary unit, there's J, but then look, this is positive J, this is negative J. So we have to put a question mark here and come back to it later. Now let's look at ZC. Notice that ZC is given by 1 over J omega C. And I've already mentioned this countless of times. Whenever you see 1 over J, right, you can shortcut this and say that 1 over J is actually negative J. So if you want to take this 1 over J as negative J, you have negative J multiplied by the rest of this. So what is the rest of this? If you extract out the rest of this, you will get here 1 over omega C. See, notice that for capacitors, it is some number multiplied by negative J. Now take a look at Z3. See, it's the same format. Some number multiplied by negative J. So that actually means that Z3 is capacitive. Now, why is 1 over J equals to negative J? If you don't believe me, this is the derivation. So to bring this J to the top, you need to multiply top and bottom by J. This and this. So J times J is actually -1, right? Because root of -1 times root of -1 is just -1. And then 1 times J is just J. Then the denominator is just itself. See? It's actually negative J and some numbers at the side. Is some numbers at the side. So whenever you see negative J, that indicates that it's actually a capacitor. Now, determine the RMS input voltage. When I look at this question, right, it was actually worth 3 marks. So if you want to do RMS by definition, which you can, it's quite painful. It's going to be quite painful, right? Because this is a sine, is a cosine, and then if you're going to do a cosine, if you want to do it by definition, so RMS is equal to root mean. So mean is given by this of the function, and then you square the function. So you have to square a cosine, and this is going to be very hellish if you do it by hand. And honestly, it's not very difficult to remember that for sinusoidal, okay, for sine or cosine, it doesn't matter. For sinusoidal, RMS values, sinusoid, oh my god, my spelling is trash. Okay, doesn't matter. For sine or cosine, RMS values is given by V0 divided by root 2. What's V0? V0 is the max voltage. And then divided by root 2. This is only for sine and cosine. If your voltage varies like this, anything other than cosine and sine, or like this, or anything other than cosine or sine, you cannot use this result. Okay, this is a special result. This is a special result only reserved for sine or cosine. Anything else, you must use the definition. So for this, what you do is you just tell them, okay, V RMS is this, and then you just plug it in. So I think the number is what? 173.2. And then the answer is this. Determine the phasor through the current, the phasor of the current and the voltage across each element. So we know that Z2 and Z3 are parallel, so let's call this ZA. So let's find ZA. So let me make some space. So that means, wait, what's 2? Is 20, right? Yeah. So this is 20. This is negative 11.55 J. ZA. ZA is equal to, so you get about this. Okay. Now you see, we can simplify this circuit. So we can simplify it like this. This is the source, Z1, and then this is ZA. Okay. So you see, we want to find the current through Zi, right? The current through Zi is actually also the current through Za. So it's the total current of the entire system, okay? The total current. So let us find the total current then. To find the total current, we need to use V equals to I Z. So this is by the source, and then this is the total impedance. So we need to find the total impedance first, right? Then we can find the current. So to find the total impedance, Z total is given by Z1 plus ZA because they're in series. So Z1 is 10, right? Plus the answer we got just now is 5.00 minus 8.66 J. You add this together, okay? So we already have Z total now. So find I using VS over Z total. VS is given by 173.2 at an angle of 0, correct? Let me check. Yes, I'm so tired actually right now. I'm really, really tired. 5.00 minus 8.66 J. Okay, and you change it to a phasor, you should get about 9.998 at an angle of 30 degrees. Okay, so that's your phasor of the current. Now we want to find the phasors, the voltage across Z1. So let's find the voltage across Z1. So to do this, let us use potential divider. So if we want to find the voltage across Z1, we need to use potential divider, which states as Z1 over the total Z total multiplied by the source. Okay, so Z1 is 10, Z total is 15. Yeah, is that 15.00 minus 8.66 J multiplied by Vs is 173.2 at an angle of 0. And this should give us there. So this is the answer for the phasor of the voltage across Z1. Now, moving on to, okay, so it's easier to find the phasor of the voltage across Z2 and Z3 first, rather than find the current. Why that? Because you look at this. Since these two are parallel, that means the voltage difference across Z2 and Z3 are the same. So, if we can find the voltage difference across ZA, then we can find the voltage difference across Z2, which is the same as the voltage difference across Z3. So let us go to the equivalent circuit diagram, meaning to say this one. If we can find the voltage difference across ZA, here and here, okay, this voltage difference, then we can find the voltage difference across Z2 and Z3 at the same time. So let us do that. So what we can say is V of ZA is equal to V of Z2, which is equal to V of Z3, which is equal to, okay, now I'm going to use the potential divider. So what I should do is use ZA over Z total multiplied by the source. ZA is what? And what's VS? So this is the answer for the voltage across both Z2 and Z3. Okay, so this is the answer. And now let's go ahead. Okay, now we need to determine the current through Z2 and the current through Z3. Okay, let me copy this diagram. Oops, what is this? Okay, so we want to find the current through here and here, correct? See, the difference across these two nodes is given by this. See, this answer we got here is actually this potential difference. Okay? Knowing that, we can use the Ohm's law. So V of Z2 is given by I of Z2, which we want to find, multiplied by Z2. So this is Ohm's law. So you see, we're going to use this voltage difference, substitute it into VZ2. Okay? So this is what? This is unknown. And then Z2 we know is 20 ohms. That means we can solve for I of Z2. Yeah, so this is our answer. And we can also find Z3 similarly. So V of Z3 is equal to I of Z3 multiplied by Z3. This is just Ohm's law. And then remember, see, it's still the same potential difference. So the potential difference across Z2 is the same as the potential difference across Z3. So it's still the same. We use 100 at an angle of negative 29.99. and this is IZ3, which we want to find, multiplied by the resistance, the capacitance, the impedance, negative 11.55. So you solve for IZ3, you should get 8.66 at an angle of 60 degrees, something like that. Okay. Yeah, I've done everything. Okay. Okay, I'm not gonna draw a Gauss plane for you. You just DIY it because it's a simple thing to do. Okay, we're gonna move on to question 4 after this.